Hello everyone, my name is Kumar Yugesh Shah. I am a PhD student at Florida International University, and I would like to present a paper about cold spray additive manufacturing, which will be a process review. A brief outline of what we'll talk about. We'll start with additive manufacturing, then cold spray. Our main focus will be cold spray additive manufacturing, then we'll conclude, have some acknowledgements and references. Moving into additive manufacturing. Additive manufacturing was introduced in the 1980s, in which the process requires the addition of materials in order to create an overall part. This industry has grown a lot over the years, in which they moved from creating only basic plastic parts to now creating high-performance plastic, metal, and composite parts. This industry initially was based on prototyping parts, and now we're not only prototyping parts, but now we're having a lot more industrial applications. One of the standard techniques for additive manufacturing is the fused deposition modeling (FDM) method, in which material is thermally extruded from a nozzle and deposited layer by layer, as typically seen in a 3D printer. One of the newest methods in the AM industry can be seen through Markforged's Metal X printer. They are using atomic diffusion additive manufacturing (ADAM), in which they are creating metal parts using a plastic spooled filament that is enlaced with metallic fine powders. They use this filament to create the part using the FDM method layer by layer, and then after that, the part is sintered to cause the atomic diffusion. Before moving on to cold spray and cold spray additive manufacturing, a brief search on these two topics. Over the last 20 years, over 2,000 papers have been written about cold spray. However, only a little over 30 papers have been written about cold spray additive manufacturing, only peaking last year at 47%. As you can see through the graph shown, cold spray additive manufacturing has been written about starting in 2015 and continuing this year as well. Moving on to cold spray. Cold spray was also developed in the 1980s, in which one of the main uses of this technology was to aid in the manufacturing of parts with enhanced coatings. These enhanced coatings allowed for an extra layer of protection against elements for these parts. The other main use of this technology was to use this as a method of repair for existing surfaces. It would allow for the repair of cracks and defects within existing parts instead of replacing them. The cold spray system can be divided into two systems, the low pressure and high pressure systems. The high pressure system is the more common and is used in cold spray additive manufacturing, while the low pressure is the cheaper and more portable one. As you can see on the figure on the left, from SST, this is an image of their low pressure system, in which you can see that it is a very small compact unit with the handheld gun on the right hand side. On the right hand side of the screen, we can see the differences between the low pressure and high pressure system, in which one of the highlighting features is that the high pressure system uses a compressed gas, while the low pressure system uses an air compressor. Moving into cold spray additive manufacturing, which is our main focus. We will start with a brief demonstration by Impact Innovations, in which they are creating a metallic flange here, which they did create on this mandrel, and now they're finishing this off with a rectangular opening. Some of the basics of CSAM. This is pretty much cold spray further developed by the additive manufacturing industry in order to create freestanding structures. As cold spray is, this is a solid state process in which fine metallic powders are embedded onto a substrate. They are embedded supersonically at greater than 300 meters per second. This is done in a layer by layer, or we can call it particle by particle fashion, in which these particles do not undergo a thermal deformation, melting, or diffusion, which is very beneficial for this technique itself. Since these particles do not melt together, the adhesion of particles is due to localized plastic deformation. This deformation allows for mechanical interlocking and metallurgical bonding during deposition. This overall aids to the reduction of oxidation, phase transformations, defects, and residual stresses in the overall part. Mostly softer metals such as aluminum and copper are sprayed. However, a variety of materials, as shown on the screen, can be sprayed as well. This ranging from titanium to aluminum alloys, including composites and refractory metals. Moving into another demonstration by Impact Innovations, we could see that this cold spray system is mounted to a 6-axis robotic arm, in which the compressed gas is met with the particles in the chamber, then extruded through the nozzle and embedded into the surface. The layout of the CSAM system is very simple, in which it consists of a 6-axis robotic arm and the cold spray system. This robotic arm holds the cold spray system, allowing for the control of the nozzle. The key parameters of the cold spray additive manufacturing system consist of the gas, powder, and nozzle parameters. First up, the gas parameters. This gas is used to accelerate the particles, as mentioned before, supersonically. In order to achieve a high particle velocity, helium is ideally used. Since helium is very expensive for production runs, nitrogen, air, or a mix is used instead. The reason helium is ideally used is due to its low molecular weight, thus allowing particles to travel faster. By having high particle speeds, allows for precise deposition and improved overall properties. Another way to increase velocity is to increase the overall gas pressures and temperatures, in which increasing the temperatures is more effective. Moving into powder, this can be categorized into 3 different categories: the size, type, and amount. The size range in diameter between 10 to 100 microns, but mostly in the mid-range of that. The type, as mentioned before, are metallic powders, and the amount is very important. It is critical to maintain a constant and sufficient flow of material, in which this powder feed rate, which is the flow of powder through the nozzle, thus affects the particle velocity overall. Moving on to our nozzle parameters, a variety of adjustments can be made, such as traverse speeds, standoff distances, and trajectories of the nozzle to achieve a precise deposition. On the right-hand side, we can see a figure of all of these aspects of this nozzle. The adjustment of all of these controls is necessary every time using the CSAM machine in order to achieve a very precise deposition. Researchers have been developing a generalized parameter paper. However, it is very hard to generalize parameters for a variety of materials and a variety of environments that this system can be used in. The quality and composition of a sprayed part has a number of key properties associated with it, such as the number of defects, the microstructure composition, as well as the overall mechanical properties of this part. These defects come in ways of micropores, microcracks, and vacancies due to particles not bonding correctly, not plastically deforming enough, and not being deposited with the correct velocity. This all can be determined by its microstructure composition, as well as researchers are using laser ultrasonic inspection devices to also see these defects. This all correlates with determining the mechanical properties. After spraying, parts typically exhibit poor mechanical properties such as poor ductility and a weaker structure. This is due to the buildup of residual stresses, which are each layer's peening stresses. A post-processing technique called annealing, which is a heat treatment, allows for the reduction of porosity and residual stresses. This also increases bonding aspects as well as overall mechanical properties. As shown in the figure, going from part A to part B, we can see that particles do recrystallize, thus allowing for the improvement of the quality and the amount of defects. After spraying, these parts are very rough in texture and might have some missing features and surface finishes needed for its intended application. Thus, another post-processing technique called machining is used, in which they use lathes, CNC machines, and milling machines to finalize parts. As shown through the video, this company Plasma is spraying a copper flange, and they are finishing it at the same time in the video. Another key aspect to the cold spray additive manufacturing system is the robotic path. The nozzle in the system is controlled through the robotic arm as mentioned before, and this is programmed through an offline program platform using CAD and CAM. An offline meaning computer developed control, while online means a person trained or guided control. This overall allows for a precise control of the robotic arm's path, thus allowing for a precise deposition. As shown through the video on the right, we can see an engineer using this 3D software to map two robotic arms. One will be spraying and one will be sprayed on. On the left-hand side, we could see in figure A CAD model of a airfoil in which the green arrows represent where the nozzle will be while printing. In part B, we'll see the finished part. This robotic control inversely affects the outcome shapes and properties of the shapes due to the nozzle's traverse speeds. As shown through the figure, while going very slow at 10 millimeters per second, we have a very great deposition amount. On the other hand, while moving very fast at 80 millimeters per second, we see a very thin deposition. When we increase the speed, as just mentioned, we do have a thin deposition. However, we also have an increasement of porosity. This is due to the fact that the nozzle is moving very fast, not allowing particles to adhere properly. However, when we decrease the speed, we do increase the density. However, we also increase the amount of residual stresses and thermal stresses within the part. By having a thicker, denser layer, results in a reduction of mechanical properties. One of these mechanical properties that's very important is the adhesion strength. By having less adhesion, allows for the delamination of layers, which is caused by the high residual stresses. The reason why we also have an increasement of thermal stresses, even though we're not melting the particles, is due to the localized particle deposition, which is at the same location because it's moving very slow, allowing for that area to increase in temperature. Another key aspect to the CSAM system is the interlayer effect. This occurs between particle and substrate as well as particle and particle. As mentioned throughout this presentation, these particles experience plastic deformation to allow them to mechanically interlock with each other. It is very important that the initial layer to the substrate is uniform and free from porosity in order to have the subsequent layers to be also uniform and free from porosity. If their porosity occurs in the initial layer or the subsequent layers, this will allow the further subsequent layers to also incorporate porosity in its layer. This will lead to poor mechanical interlocking as well as poor mechanical properties overall. Moving on to the applications of CSAM, beyond the simple metal pieces that have been created since this technology has started, researchers have also used this technology for metal matrix composites, in which they're spraying nanoparticles, the creation of magnets for electric motors, as well as creating heat sink fins for optimal heat transfer. As shown in the top left corner of the screen, we can see these heat sink fins. In part A, we see the overall view of them, in which they have a diameter of 1 millimeter, and in part B, we can see the cross-sectional view of them. In the first video, we can see two 6-axis robots being used to create a helical magnet inside a hollow cylinder for these electric motors as mentioned. In the second video, GE is showing off their system in which they're creating a helical gear on top of a cylindrical rod, which only took 9.5 minutes to create. Some other applications to the CSAM system are creating parts with materials that are sensitive to higher temperatures, such as nanocrystalline and amorphous materials. As cold spray was intended for initially, they are using this cold spray additive manufacturing system to repair damaged parts, welding parts together, as well as additional modifications. Major manufacturers, the aerospace and automotive industry, and the military mainly use this system not only to create parts, but to repair damaged structures. Some of the damaged structures include crucial fighter jet components, as well as basic vehicle frames, instead of replacing them and wasting a lot of money. As shown through the figure, we can see a basic aluminum vehicle frame being repaired for its use. Some of the newest research being done in CSAM include 3D modeling and simulating of the entire unit, more specifically the particles leaving the nozzle and being embedded to a surface. This is being done to understand the limits and challenges of the entire system to overall improve the quality of deposition. Not only that, but neural networks are being used to determine profile prediction to overall optimize the geometric control of the robotic arm while depositing. The cold spray additive manufacturing system encompasses a very complex algorithm in order to control these robotic arms precisely. As shown through the video, GE is showing off their two robotic arms, making it 12 axes of freedom, in which they're creating a complex airfoil. They're doing this through complex programming and deep learning for these robotic components, as well as with AI and machine learning, in which they're using a real-time 3D scanner to determine the current layers being printed and the defects within to determine how the subsequent layers will be printed. Moving along to a brief conclusion, additive manufacturing has grown a lot in the last 36 years of existence, in which cold spray additive manufacturing is one of its newest processes. CSAM uses the fundamental understandings of the cold spray system, which was developed in the 1980s, and it can be agreed upon that this is a very emerging technology. It can also be agreed upon that this technology will expand for the next 5 to 10 years, in which not only will they be using it to manufacture goods, but it will be also a replacement manufacturing process for manufactured goods. Move along to acknowledgements. I would like to acknowledge Dr. Argivald, Dr. Zhang, and Dr. Tansel, as well as the overall Mechanical and Materials Engineering Department for the continuous support. Moving along to our references. I have also included my email for anyone that wants to reach out to me. Thank you so much.